All right, hello everybody, and welcome to the Hydrogen and Low CO2 Iron and Steel Making webinar series. This is the third webinar in this series, and today's topic will focus on steel making with zero carbon iron units. I have a few things. I'm Anna Voss with AIST, and I have a few things to go over first before we start the webinar. And particularly, these are our antitrust guidelines. So I'm going to read these real quick. Do not discuss with others or your own or competitors' prices, pricing procedures, or anything that might affect prices such as cost, discount, terms of sale, or profit margins or anticipated wage rates. Do not make statements about your own prices or those of competitors. Do not talk about what individual companies plan to do in particular markets or with particular customers. Do not disclose to others any competitively sensitive information. Do not propose or agree to any action intended to disadvantage or injure another company. Do not stay at a meeting or activity where any such anti-competitive talks occur. Also, our anti-harassment policy. The Association for Iron and Steel Technology is dedicated to providing a harassment-free event for everyone, regardless of age, race, religion, disability, gender, gender identity, or sexual orientation. We do not tolerate harassment in any form of anyone attending an AIST event. Harassing behaviors include offensive verbal comments related to age, race, religion, disability, gender, gender identity, or sexual orientation, the use or display of sexual images, activities, or commentary in public spaces, deliberate intimidation, stalking, or following, harassing photography or recording, sustained disruption of events, or inappropriate physical contact. Participants asked to stop any harassing behavior are expected to comply immediately. Participants violating this policy may be sanctioned or expelled from the event or the membership at the discretion of the AIST leadership. So with this webinar, I wanted to give you as attendees a heads up that your audio is currently disabled. And if you do have any questions that you would like to ask the panelists, please use the question and answer feature, or I think it's listed, the button actually says Q&A. If you look at the bottom of your screen or the side of your screen, a menu will pop out and you will be able to type in your question there. The host and our moderators will determine which questions are presented to the panelists to answer. This session is being recorded and it will be available on our website shortly after this broadcast is done. And if you have any technical difficulties, feel free to email training@aist.org. So with that, I'd like to introduce our moderators. We have Chris Pistorius, who's the POSCO Professor for Materials Science and Engineering and the co-director of the Center for Iron and Steel Research at Carnegie Mellon University. Also, Jose Noldin, who is the General Manager of Product Development at CSN. Jose apologizes he's unable to join us today, but has been helping out with this webinar series and helped out in the inception of it. So with that, I will turn it over to Chris to introduce our three panelists today.
Thank you very much, Anna. As Anna said, my name is Chris Pistorius. I'm currently chair of the Direct Reduced Iron Committee of the AIST, which has been hosting this series of three webinars. Just a few words about the past webinars. You can find those on the AIST website. If you go to conferences and events, and then webinars and past webinars, you'll find many there. The AIST collectively has been really busy with putting these on while we are all limited in how we can meet. So the past two have been on June 9th, one on iron making with alternative reductants with quite a strong focus on hydrogen. Then on June 23rd, there was one on the production, storage, and safe handling of hydrogen, looking quite globally at the current situation of steam methane reforming to current green hydrogen production and possible future green hydrogen production. So today's webinar then looks at how we think it might be if this low carbon material potentially from hydrogen reduction becomes available more widely and is used in steel making as part of an aim to have a low or zero carbon steel making operation. This changes many other ways in which electric arc furnaces have been operated recently and really have improved their efficiency markedly by using carbon to do quite a few jobs in the furnace. So as you see there, we've got a nice lineup of speakers here from 3 different continents to talk to different parts of it. So I'll briefly introduce all of them and then just allow them to carry on with sharing their slides. Just briefly, how the format will go, each of them will have a few slides to give their main thoughts. Then we'll have a series of questions. I have some pre-prepared questions, but certainly whatever you post via the Q&A button, I would be very happy to look at and submit to the panelists. So first up will be Jeremy Jones, who you see there is the managing partner and founder of Continuous Improvement Experts. He's an international expert on electric arc furnaces, and he's really very well known as a lecturer on electric arc furnace steelmaking at various AIST events. So very well qualified to talk to this particular application. Following Jeremy will be Jorge Madias. Jorge is a director at Metallon, which is a consulting and training company for the steel industry based in San Nicola, Argentina. The focus of Metallon is on electric arc furnace plants that produce long products. So again, exactly in line with the particular application we're interested in. And then from Australia, we have Jeff Brooks, who has a long and varied background in studying the fundamentals of iron making and steel making operations and many other things. According to the Swinburne University's website, he is currently the Pro Vice Chancellor of Future Manufacturing, that's right, Jeff, which basically means coordinating research and teaching relating to manufacturing across the whole of Swinburne University. So excellent lineup of speakers. Thank you very much to all of them for giving up their time and especially a late hour in Australia for Jeff. And I'll ask Jeremy to start us off, please.
Okay, so this morning we had a number of questions ahead of time as sort of a guideline. And one of them was, well, what are the greatest challenges for carbon-free DRI and EAF steelmaking? Well, in general, as we try to move towards this low carbon footprint steelmaking, what we need to do is return to a lot of the fundamentals and understand why various technologies were adopted and adapted into the EAF. And how do we provide that same functionality without carbon-based materials? So this involves things like the reason why we put burners in an EAF was that we were trying to eliminate cold spots so that the scrap melted in more evenly and we could achieve an efficient endpoint, achieving the temperature and carbon level in the bath at the same time. So if we don't use fossil fuel to provide energy at those cold spots, or do we use hydrogen-based burners? Do we use maybe ammonia-based burners? Do we use plasma torches? There are a number of different options which we'll have to look at. But what happens when you remove a lot of the chemical energy from the furnace is that we're going to require a lot more electrical energy. probably on the order of 500 to 550 kilowatt hours per ton of liquid steel. And that isn't an issue because we're assuming that by the time we do this, we'll also have renewable energy. So our electricity won't have a carbon footprint. And then we have to consider other factors such as iron yield, which are, is closely tied to the carbon-oxygen iron balance right now. But in the future, we'll have to see what our options are for recovering iron from the slag and factors such as that. Some alternative melting technologies have been proposed, including induction melting, but currently induction furnaces are limited to about 60 metric ton heat size, so that wouldn't really be suitable for a lot of product lines. But we'll have to look at it. There will be some application in smaller sized facilities, maybe some more specialized ones. But moving forward, I think the EAF is a preferred technology, but it's going to go through an evolutionary process. And I think Geoffrey's going to talk about that a little bit. We could try to come up with a hydrogen-based pyramid process. And there have been, obviously, in the past, hydrogen-based direct reduction processes that have been implemented commercially. Again, Geoffrey's going to talk about that a little. And then we also have to consider exactly how we're going to feed these various processes, because over the past year, we had a shortage of DR grade iron ore pellets. And that's definitely, as we try to expand the implementation of direct reduction further, that's going to be a big issue. Though some people have proposed that we use lower grade pellets with high gangue and then pre-process those in a submerged arc furnace in order to eliminate the impact on the EAF, or at that point it could be a BOF as well. With respect to scrap or carbon-free DRI, the choice is really a function of what you're making and what you have available. Until we find a way to remove residuals from scrap, ore-based metallics are going to be required to enable a circular economy in steel. If you look at the projections in the developed world, the generation of prompt scrap is projected to stay fairly constant throughout to about 2050, while the amount of obsolete scrap that's coming back into the scrap supply is growing quite considerably. So we'll have to figure out how we use that. We also need to do a better job of designing products to remove things like free copper from the scrap. Because, for instance, if you remove all of the free copper from an end-of-life vehicle, you can probably produce a shredded scrap with about 10 points of copper. In reality, we see shredded scrap with copper levels ranging from 15 points to as high as 35 points. So obviously, in some cases, we're doing a very poor job of removing the free copper. And the free copper is that copper that's not tied up directly in the steel, but is in other components in the material that we're processing. Several people have looked at biomass as a foaming agent. People have used things like coconut shells and agricultural waste in Indonesia. It was fairly common to see people use roasted coconut shells as a source of carbon. So definitely people are looking at biomass as a substitute for coal. But to truly be carbon neutral, we need to grow it as fast as we consume it. So that's something that we'll have to consider. These materials can be effective for slag foaming, but of course, things like parameters such as size, ash content, and the fixed carbon all factor into how effective these materials can be. There's a lot of work done at University of New South Wales on recycled plastics, and they found they could substitute about 30% of the injection carbon with plastics fairly effectively. But the issue is that the plastics break down much more rapidly than carbon does. And so you're limited as to how much you can use because you get a surge of gas generated. And of course, all of these things, the slag foaming is important. We don't actually remove nitrogen from the bath through slag foaming operations, but we definitely prevent the pickup of nitrogen, and we prevent air nitrogen from passing through the arc and getting ionized and traveling back into the steel bath. The other options for managing arc coverage, we've got several. We can foam with gases other than CO. We could operate with more slag mass and design the furnace to carry over a greater amount of slag, because it doesn't matter how we bury the arc, just that we bury the arc. Of course, a larger slag mass would be a slightly greater heat sink, but it could be manageable. Of course, if you're working with some materials that contain a lot of phosphorus, then it becomes an issue, because you have to flush the slag in order to get the phosphorus out of the steel and out of the system. Some of the other options, people are looking at various hydrogen compounds, materials such as zeolites. Basically, we need to find materials that break down completely at steelmaking temperatures, that don't impact the quality of the steel, and that generate a lot of fine bubbles. So there are several options that people are investigating right now. And of course, there's always the option of continuing to use carbon and using carbon capture and sequestration. Currently, it's not a commercially viable option, but as we enter a period where we might be faced with carbon taxes, then things like that will become more attractive. Overall, I think in the future, it'll be very important to have a broad base of raw materials to draw upon, because you need flexibility in order to meet the desired EAF cycle times to match the rest of the plant in order to get efficient operation. People have already shown that blending materials allows for lower overall operating costs by taking advantage of materials that are closer to the plant and that are readily available. But all of this comes back to developing the right tools and understanding the carbon footprint. And at CIX, we've actually been doing that. And we've been working with several European plants to develop a model that allows them to quickly evaluate different operating scenarios and options with respect to the carbon footprint. And that's what I've got for now. I'll hand it back.
Thank you very much, Jeremy, for setting the scene for us. Next up will be Jorge, who actually has some examples of the use of low carbon materials in EAF steelmaking. So Jorge, please go ahead.
Okay. Sorry, thank you for the presentation. Okay. Okay. Morning, everybody. A lot of food for thoughts from Jeremy. I will show some other things. Some of them will overlap a little bit with Jeremy's talking. This is where we are today regarding CO2 emissions. Some in average 44 kilograms of CO2 per metric ton of steel. Looking at carbon in the bucket and injected carbon, some 10 kilograms of CO2 per ton of steel from natural gas, and then 4 to 7 kilograms of CO2 per ton of steel coming from electrodes. Then we have, of course, other carbon sources as scrap, DRI, pig iron, carbonates, etc. I will go back to old times, as I am the oldest speaker here, and to the paradox of coal-based low-carbon DRI. When we work with the kiln to make sponge iron based on coal, what we got was low-carbon DRI. 0.1 was normal, because when the temperature is okay in that kiln for recarburizing, the atmosphere is not okay. And then the opposite situation. When the atmosphere is okay, the temperature is not good for recarburizing. So we usually get low carbon in there. And in Latin America, we have had 3 plants, 5 units, Gerdau Charqueadas, what used to be Asofinos Piratini, SBQ producer, Cider Peru, and Aceros Arequipa, both in Peru with 2 units. Regarding Piratini, they had DRI from pellets and lamps, EAF melting with carbon from pig iron, as is usual in Brazil, and carbon injection with lances. Then further treatment in ladle furnace and vacuum degassing, ingot casting, and SBQ. They were, of course, they were not very happy with that low carbon 0.1, but they worked for 2 decades this way, till the DRI plant was idled. So 2 decades with low carbon DRI. In the case of Aceros Arequipa, it was the DRI was made of blast furnace pellets, curiously from Shougang, blast furnace pellets, not DRI pellets, and lamps for several local sources. It was also 0.1 carbon. Lot of R&D from their people to get higher carbon, testing natural gas injection at the end of the process, but it was very slow and somewhat expensive, so it was not practiced for a long time. They melted this low carbon DRI with the so-called closed door process by Jorge Eugene, the steelmaking manager at that time. 40,000 tons the furnace, 45 MVA the transformer, 3 supersonic lances, and they used to charge 1 bucket HMS, then slag door closure before flat bath, continuous charging of low carbon DRI, and at times they also continuously charge shredded scrap. Anthracite lamps to favor slag foaming. They used to have some kind of BOF-like sloping in some heats through the holes of the roof. Low FEO in the final slag, the EAF. So they worked like this for several years. And then we have the India experience, which they are still working today on this with large number of coal-based DR producer, some melting with EAFs, other with induction furnaces. Of course, we can't avoid to remember that with induction furnace, we get rid of graphite electrodes, natural gas, bucket carbon, injected carbon, but of course there is some issues like the use of anthracite and pet coke for reduction of FeO in the DRI. That is important stuff. You always have some percentage of FeO in the DRI. You build acid slag that must be removed during the process coming from the gang of the DRI. You could need some dephosphorization or decarbonization. This is today carried out in some plants, only a few plants with downstream oxygen stands to that purpose. And then we have the scale problem as mentioned previously by Jeremy. He mentioned 65, the largest inductotherm furnace for steel. According to the inductotherm guys, they say scaling should not be a problem, but I don't think that to be so easy. This is a must, as Jeremy showed. By one side, we always have higher energy consumption with DRI, but then if we get rid of chemical energy, it should be more high even. So hot DRI charging should be a must for lowering power consumption, say 100 kilowatts hour per ton, less than normal. So we will be in that case close to the numbers of scrap-based furnaces. We have different transport systems there for existing and for greenfield plant, mechanical conveyors, transport vessels, as it used to be the first time I remember in Rio de Janeiro, in Cosigua plant from Thyssen, the Puroffer process with bottles under nitrogen to transport the DRI, pneumatics or gravity, which looks very nice for this purpose, as it looks like the one which has less, shorter way from the module to the furnace, and so maybe lower heat losses. Use of biomass from the European experience with lab foaming trials, pilot EAF in Germany, and full-scale tests in Ferrieri Nord. In Ferrieri Nord, charging buckets was okay, no problem, but in Georg-Marienhütte in Germany, charge injection gave poor results. They thought of some re-engineering for the injectors. There was issues with, besides what Jeremy mentioned, ash size, there was also issues with density and so on. West tire that was mentioned by Jeremy practiced in 6 plants coming from Australia. Maybe there could be some replacement of natural gas by hydrogen. Alternative foaming agents also going to the past. There was at the beginning of this century some calcium nitrate co-injected with carbon proposed for stainless. I don't know if it is still in use. Of course, in stainless you had the problem of low FeO in the slag, so Norsk Hydro had a byproduct from fertilizing industry, and they made trials and tests in several stainless plants in Europe in the first decade of the century, getting some good results with this agent, just as an example of what had been done in the past with alternative foaming agents. Okay, this is all I have for today. Thank you very much.
Thank you very much, Jorge. Just as a comment from a little bit of work I did on the SLRN DRI, is not only is it low in carbon, it's also high in nitrogen. It contains maybe 150 ppm of nitrogen, so not an ideal material for steel making, that's for sure. Next up, Jeff Brooks. Jeff, please go ahead.
Good morning for anybody in Australia, and good afternoon, good evening, sorry, and good morning to everybody in North America. I would say straight away that if any of my PhD students are up, would you please go to bed? It's too late to be up listening to these talks. But I'll try and add a little bit to what my excellent colleagues have already said. So let me just get the share screen going, and we can go through a couple of slides. All right, let's just get that into the right mode. All right, so let's talk through some of the basic things. Just summing up a fair bit what's already been said. Obviously, if we have a very low carbon iron source coming into EAF steelmaking, we have less steelmaking to do, all right? So that has some productivity repercussions. and also has some potential to be a good thing, right? We just basically have less steelmaking to do, because actually the removal of carbon is actually a reasonably slow process in steelmaking. And in fact, a lot of what's going to happen if you have a very low DRI, if you have a lot of low DRI, low carbon DRI coming into a process, you're going to be melting and then basically taking away molten oxide. So you're really reducing the steelmaking somewhat. But you're also going to bring less chemical energy into the AF, which has already been discussed quite nicely by my colleagues. And you've got to take that into account. And as just explained, you've got this whole issue of flushing. And I thought Jeremy explained that very clearly, that you basically have this issue of, well, where are we going to generate bubbles, low in the melt, so we can get rid of the nitrogen? So that could be a real issue. And we've already had a nice discussion about slag foaming. And I noticed that one of the people who's raised a question already said, oh, surely this is going to increase oxidation, FeO in the slag. So I think all your professors that taught you will be very, very happy that you remember that relationship between low carbon and FeO, and that logic of that is sound. So basically, we're going to have very low carbon in the melt at some stage. That is likely to generate high FeO in the slag. So we're going to have to do something about that. So these are the issues that you've already heard a bit about, just to sort of sum them up in one slide. And just to remind you a few basic things that need to be brought out. If we go for the idea of trying to lower a carbon footprint of steelmaking by using hydrogen, that's only one part of this process, because we know that if you put more DRI into an AF, you generally speaking increase the energy usage. Now the graph I've got here is a bit idealized. I don't think it's quite as neat as that. That diagram makes it look very neat, but it's a more complicated story than that. But basically, the more DRI, the more energy your CO2 you're going to generate with the existing technology. So you're going to have to look at the whole system. You're going to have to look at, as Jeremy mentioned, you know, how's electricity generated? What's the chemical energy we're bringing into the AF? So I think just looking at the iron and we're making a hydrogen, therefore that's great, is too simple. You've got to look at the whole system, and that's something that's going to be important. And the other thing that's also come out, was very nicely brought out in the previous ones, is that, you know, DRI is not DRI. There are many types of DRI. And I have here a table here from a paper by Hornby Anderson, and, you know, and she's got like 6 different types of DRI there. And you can see quite a large variations in the carbon, variations in the gang. And that's going to be the same if we go down this route. If we have a lot of hydrogen production of iron, we're going to have all sorts of variation in the chemistry, depending on the ores, depending on the route. You know, it's going to be another complex story. It's not going to be all the same. So, you know, take that into account. When we're talking about DRI, we're talking about, you know, in a very generic way. There's a lot of variety in DRIs, as I'm sure many of you are aware. And I think I noticed that one of the questions already, I think Phil Mackey, he's asking us about the energy balance. Well, if you look at a typical AF, you know, you get something around about 50% of the energy coming into the EAF is typically chemical energy. So if we start taking carbon out, that's going to affect that balance, and we have to complement it up with some electricity, as Jeremy had a guesstimate on in his slide, and he's probably right. So we're going to have to push the electricity up or find another energy source if we take the carbon out. And on the right-hand side there, I couldn't resist being a professor. I put some thermodynamics in there, of course I can't resist. And it just reminds you of some of the energy associated with the different reactions. And you can see that carbon and silicon provide a lot of energy, particularly if you take the carbon to the CO2, right? Now you get a lot of energy. Now, we all probably know that EAFs, it's hard to recover all that energy of the post-combustion, but you are taking a lot of energy out of the system if you take carbon out. So you're going to have to redo your balance. You're either going to have to push up the electricity, or you're going to have to bring in some other energy source, all right? So that's just looking at you know, the basic logic of what would happen if we had a low carbon iron coming into our EAFs. Now, fortunately, we do have some significant results to look at. That's there has been people who have made significant quantities of basically zero carbon DRI. And this is the Circured process, which was operating for a number of years. It was developed as a fluidized bed process, and Outokumpu were developing it, and in Germany, and then it went over to Trinidad, and it operated there for a number of years. All right, and this process, it's a fairly complicated process. You always find that when you try to replace the blast furnace, you always end up with this quite complicated system, because you've got to get a lot of steps into you know, you've got to replace a lot of steps that you have inside a process like the blast furnace. And this process has, you know, a couple of different fluidized bed steps, and one of the fluidized bed steps is got quite high speed gases. So basically what's happening is you're getting rapid reaction, and then when you're trying to get to the final high metallization, they had a slower moving bed, and you can see they've got this stage 2 in the middle of that diagram. And from that, they got up to metallizations of about 95%. Now, this process in Trinidad, it used natural gas as the source to make hydrogen. So it was, you know, basically, I'm sure many of you are aware, there is quite cheap natural gas in that part of the world. So they were able to use that cheap source of hydrogen to, you know, put hydrogen into the process. One of the things that's very interesting about this process that I find I want to know more about is that they report that by using hydrogen, they had less problems with sticking. So I'm sure many of you would be aware that one of the bugbears of using a fluidized bed for making DRI is this whole issue of sticking of ores. And so, yeah, that's a result that's very interesting. And I'd like to myself scientifically explore that a bit further. Anyway, they produced significant quantities of a HBI from this process, which was then sold to various smelters. And so there's quite a lot of accumulated experience from that work. They produced over 300,000 tons in the paper that I can find on it, the most detailed paper. And so this paper, I've put the reference down there. So I suggest all of you who are really interested in what happens when you put zero carbon DRI into a process should read that paper. And they reported that if they injected carbon into the slag, so that problem that has already been brought up on one of the questions in the Q&A section of this talk about what would happen with the FEO, they had to inject carbon to keep the FEO at a reasonable level. So I would describe 28 to 35% as well, relatively high FEO, but not unacceptable depending on your slag volume. So they had to put carbon in. And they also had to inject carbon and oxygen to keep the FEO down, but also assist foaming. So they found it necessary to have some carbon and oxygen coming into the system. And they also found that when they used a large amount of DRI to compare to scrap, that it was best to feed continuously into a large heel, which makes sense, right? So you have a big pool of molten metal, you try to feed continuously or semi-continuously into that large heel. And when you do that, they mentioned it's very important that you have to match the feeding to the heating so you don't get large icebergs, all right? So you're going to have to pay some attention to matching the heat input to the heat requirements, because you have the potential for a whole lot of unmolten iron sticking together and forming an iceberg, which is not desirable in an EAF, of course. So that was the general experience that they reported in that paper. And it makes sense. All those things make sense to me. And they do a diagram where they sort of put out the importance of, you know, making sure you get some carbon and oxygen deep in the bath so you can stir the bath, help flush out the nitrogen, as we've already been discussing. And they also advocate putting carbon into the slag. So you can see straight away your desire to get rid of carbon from the process is compromised by all these requirements to you know, remove nitrogen, foam the slag, etc. And they report some hard data in that paper. So I do suggest that some of you look at that, would like to know the details. So my conclusions are, or my thoughts at this stage, I don't think it's too early to have conclusions in this area, but my thoughts are, well, you know, clearly on a brownfield site, if we suddenly built a hydrogen iron making process tomorrow, it's operating tomorrow, and we tried to bring that feed into an AIF, we obviously need to redo our energy balance. We're going to have to bring in some other energy from somewhere, and we better be careful about what the carbon footprint of that energy is. Otherwise, why are we bothering with all this hydrogen production of iron? We have to be conscious of that. We're probably going to have a large heel, and if we don't have a large heel operating, I reckon we're going to have lower yield. All right, so I don't think we're going to start losing a fair bit of FEO at some stage. I think on the positive side, we should be able to push up productivity. You know, we've got less steel making to do. We have less stuff to do. We should be able to push that the iron quickly through the process if we've got everything organized well. Obviously this productivity issue that needs to be, you know, properly explored, but there are real potential, I think, for improving productivity. Now, if we go the other way and we imagine we're starting again, right? We've found some very friendly investor to build a whole new process around this low carbon DRI. Well, now I think we need to rethink the whole thing, all right? Because basically, when you look at this low carbon DRI, there's not a lot of steel making to be done. So we shouldn't, we should be able to get some advantage from that. And I actually start questioning whether, in fact, we need to have two separate processes anymore. Do we need a separate ladle process after the melting? Like, if we have that little steel making to do, why don't we think about putting them together? I don't think that's a ridiculous notion. I think you could imagine collapsing two steps into one. I think that you could get very good high productivity if you really, you know, start thinking about ways of designing the process around that feed material. And you might even be able to have continuous output. I remind you, everybody, we have steel making. I love steel making. I've been working on it for a long time, but it's a batch process. Everything on either side of it is continuous. You know, most good iron making processes are continuous. Casting is continuous. Rolling is continuous. It's us steel makers that want to cook things in batches. Well, there is a possibility that you could turn this into a continuous process by having some, you know, innovation in how you refine the steel before it goes into the tundish. So I think if we're going to have a greenfield site, we should rethink a lot of these things, and we can perhaps find some big advantages to productivity and the size of equipment. All right, I hope I haven't gone through too many ideas too quickly, and I hope I haven't contradicted my friends and colleagues. I think we've been relatively consistent with our story, but I think there's lots of interesting issues there that to look at, and I'm looking forward to the questions.
Thank you very much, Jeff, and thank you again to all our speakers. We now move into a period of question and answers, and we've had some excellent ones from the audience, so please keep them coming. I'll start with one for you, Jeremy, and it's a slightly rephrased audience question, and it's about what we need to remove nitrogen from the arc furnace, and the question talked about different carbon-bearing materials like recycled plastics, how good they are at removing nitrogen, and so my question is, or request really, is just to briefly talk us through what we really need to remove nitrogen as as a basis for, would any of these other things work at all?
Yeah, so just to sort of reiterate, and Geoffrey hit on this, sort of reinforce what I had said. When we're slag foaming, the slag foaming operation doesn't remove nitrogen because generally speaking, we're having a reaction at the bath slag interface, which is where the FeO tends to concentrate. And so we're injecting a material. Our objective is to get it to spread out across the bath surface and then generate a lot of fine bubbles, which helps to foam the slag and shield the arc. We do see a benefit with ore-based metallics because they dilute the nitrogen content. Ore-based metallics typically have 10 to 20 ppm of nitrogen, whereas some scrap can be up as high as between 100 and 120 in the worst case. Obviously, things like busheling are much lower, probably 40, 50 ppm. But if we actually want to remove nitrogen from the steel bath itself, then we have to, traditionally we've generated CO by injecting oxygen into the bath, having it react with carbon, and the nitrogen is stripped in those CO bubbles that are generated. And so we can't really get rid of carbon entirely. And even if we could, then we wouldn't be making steel anymore, because I think by definition, steel is an alloy of iron and carbon. Is that correct, Geoffrey?
Yeah, you're on the money, mate.
Yeah, there you go. So we can't eliminate it, but we do have to come up with some different ways of thinking this. And what's happened is in a lot of flat product producers now, it's very common to have tank degassers, and so nitrogen hasn't been as big an issue the last 10 years or so as it was prior to that. But there was a lot of work done by SMS where they looked at the ability to get down to tap nitrogen levels of 10 to 20 ppm by using large quantities of ore-based metallics. So it's really going to depend a lot on a particular operation, what they have available, and they'll have to evaluate their options.
Thank you very much. Then one for Jorge, again, a lightly reformulated audience question. And this is something you covered a bit in your presentation, but maybe talking a little bit more to how do you think dephosphorization strategies would change? Because all kinds of things may well be different. Slag composition, if it's the same DRI, the load of phosphorus, if it's the same iron ore pellets, the load of phosphorus should be similar. But the conditions in the furnace are likely to be quite different. So if you can please talk to what do you think appropriate dephosphorization strategies would be?
Okay. Thank you very much. One thing to be taken into account is what we have been seeing in the plants, in the DRI plants for the latest, say, 10 years or so, at least those which depend on ore from Brazil, from Samarco and so on. We have been higher and higher phosphorus content. So that is to be taken into account as we will be, in the case of all this is concretized, we will be seeing much more use of DR pellets, and there is not so much supply of specific DR pellets. And if the phosphorus was growing in the latest, say, 10 years or so, I imagine that it will grow more, so we will have maybe more charge of phosphorus in the furnace. Then we have, as mentioned before, FEO already charged in is much FEO in the DRI than in the scrap, so it should help a little bit for dephosphorization. We usually have, say, 8% FEO in the DRI. It should be of help, I think, for that purpose. I don't know if there is another thoughts by Geoff or Jeremy on that.
Yeah, I think that my dream at the end about we could have not much steel making and maybe revolutionize the process. Yeah, phosphorus would be a big sticking point. Phosphorus is not an easy element to remove. So I think that will require some, steel making, and that one, fluxing and getting the balances right. I suppose you might have an argument for deslagging, because you're probably going to have high FEO at the start of any process with this much low carbon DRI coming in there. So high FEO means you can probably remove a lot of phosphorus. You might have an argument for trying to scrape off some of the slag at that stage, and get the phosphorus out of the system. But I think that question about phosphorus and how we're going to deal with it is something that is, will need quite a bit of work, because I don't think there's enough experience from the previous work I just reported to really know with confidence exactly how you're going to deal with it. But I suspect you're going to have a good phosphorus early on when you have high FEO. This is what I would expect.
Yeah,
Thank
that's
you.
also when things are the coolest, because you also get the temperature reversion. So yeah, it's complicated, but that's one of the biggest challenges, I think.
Thank you. Jorge, just there was one follow-up from your presentation, which I think we can take now, and this is specific question about this low carbon coal-based material. Is did they encounter any issues with reoxidation of this material before it was fed to the arc furnace?
Okay, yes, I think so. In those cases, they were captive plants, so there was not too much time in preparing the DRI, then using the DRI. Not too much time delay. It was small facilities, not so much DRI production, but it was short time. Of course, I think we should have problems, but I don't remember any fire. I remember much more fires in plants using two points of carbon in the DRI rather than in those plants using almost no carbon in the DRI.
I think that's related to the porosity. If you see the different products, and Chris, you've probably looked at that.
Right. Yeah. The coal-based DRI, because it's produced at a much higher temperature, around 1200 Celsius, has actually a much lower specific area. So it is actually a bit more stable as a material. So Geoff, question for you about this whole idea of using biomass as a way, potentially carbon neutral way. One issue with that, of course, is that it takes some time to grow this material. So unless it's a waste material, of which there's only so much available close to the plant, if it's trees that need to grow again. We did this here in Pennsylvania. We had charcoal-based iron making in the 19th century. And it took about 100 years for those forests to grow back. So you have a carbon debt for 100 years. So what are your views on the feasibility of using biomass as a slag foaming agent, as a partial replacement for fossil fuel carbon?
Sure. All right. Well, I first of all have to reveal my form on this. In my younger and more idealistic days, I worked for 3 years on developing a biomass-based iron-making process, and we built quite a large pilot plant. And so I've been in this area a lot. Look, biomass is, as you say, if you can match it with the growth, then of course, you've got a carbon neutral effect. But whenever we look seriously into this, and it's been advocated in Australia and in Europe and other places, you get into this very strange political situation where you're asking people to say, let's grow forests so we can feed the steelmaking process. I think that's politically naive to believe that's going to happen. It's theoretically possible. It's theoretically possible to imagine that you could have a forest the size of Belgium to maintain the European steel industry, but I don't think it's politically impossible. So I think it's some very localized area, it could work. Yeah, I can imagine some part of the world it could happen, but I don't think it's a general solution for our industry. I really believe it's politically impossible. I just don't see the public going along with that idea of growing forests so we can have a steel industry. And I think that's one of the exciting things about this hydrogen economy. If you think about it, and we're all fans of the steel industry, it is a great industry, but, what are we going to do to lower the carbon? So if we could find a way of making hydrogen cheap, and I noticed that Sarah Hornby's already raised the question about, is there a cheap way of making hydrogen? And that's the big issue, right? But if we could find a cheap way of making hydrogen, we could decarbonize our industry. And I think that would be both environmentally and politically much easier to sell than saying, let's have some huge forest to maintain for the steel industry. Sorry to give a political answer to a technical question, but I just think that's my experience of it.
Yeah, if I could just inject there, Chris, I think in Brazil, the mini blast furnace industry has come the closest to achieving this. And if you've ever visited, it's quite considerable the way that their reforestation with the eucalyptus, which is very fast growing, but it's very involved. And as Chris says, involves a lot of real estate. So definitely some things to be considered.
Yes. I would like to add one thing is a blast furnace based on charcoal with 600 kilos per tons, which is a lot. I think it is just possible in some parts of Brazil and maybe in Australia because eucalyptus comes from there. But if we talk about electrical furnace replacing carbon materials for injection, they are smaller numbers. I think maybe it is possible. It's just a small number, not as big as for whole iron making based on biomass. No?
Okay, thank you. We are coming close to our scheduled end time. I think we've got time for maybe one last quick round of questions. Jeremy, I have one rather specific audience question for you, which is, if we do use hydrogen-based material, it's essentially pure iron that we're feeding, which apart from not containing carbon, then has a much higher melting point than some of the high carbon DRI that's being used, that is close to being a pig iron with a melting point of 1150 Celsius instead of 1500 Celsius. Do you think that'll make a difference in terms of how one can feed and melt and avoid ferroburgs in the furnace? Yes,
so that's exactly right. And Geoffrey touched on this. So I was involved in all of the trials for Cliffs with the material from Circa Red in Trinidad. And we actually, when we put the material in the bucket, we layered it close to pig iron because we found that we got a better yield that way. And we recovered, it melted in faster. We didn't see the variations in the FEO and the slag because we were taking care of it in the bath. If you're top feeding the material, definitely what you've got to look at is probably running with the bigger heel, as Geoffrey has said. But also one of the things I've been looking at, even for DRI and HBI feeding now, is that, is it possible to go to higher feeding rates by feeding at more than one point? Because when we feed at a single point, we're only really taking advantage of the thermal conditions at that point. If we feed at 2 points, we should presumably be able to feed at a higher combined rate. As I said, what I expect to happen is that the design of the EAF is going to evolve. It's not going to stay exactly as it is right now. We're going to start to look at these things, understand the fundamentals, and basically evolve the design of the EAF to match the materials and the different conditions that we're going to experience.
Can I just add to that? I think that, you know, if we have a lot of low carbon iron suddenly being produced, you know, continuous feeding into flat baths or semi-continuous feeding into big baths is the obvious way to go to avoid a lot of problems, right? So, and I think that that would be part of the change in the process that Jeremy's talking about. You'll start seeing, I predict that would be a big shift in the way people operate. Of course, you're seeing that happening already in quite a few plants. There's a number of plants around the world that kind of operate on that philosophy already. So, you know, but you would see more of it, and you would see a greater evolution, I think, in that direction.
Yeah, and we might change the size of the briquette, Chris. We're not locked in on these larger briquettes that we have right now.
Excellent. So thank you very much. I think that is what we have time for. Thanks again to our audience for being with us and for the questions, some of which we managed to address. And thank you again to our speakers, Jeremy Jones, Jorge Madias, and Jeff Brooks. For Jeff, I believe it is some early hour of the morning there. So thank you for staying up and staying with us, and everyone for your contributions. As Anna mentioned, this webinar will be available on the AIST site soon. So if you want to recap any other points, look at some of the slides in more detail, that will be available. There will be other activities forthcoming from our DRI committee. We have a committee meeting that will likely be on September 2nd. That involves both technical committee matters, but also presentations. And then we have a conference coming up. We hope in person in March of next year on production and use of DRI and HBI. So again, thank you very much. And
Chris, could I just say something quickly?
Yes, please, Jeremy.
Would it be possible for the questions that we didn't have time to answer, if AIST can collect those? I'm pretty sure that myself and the other panelists would still be interested in providing some answers. And the other thing I'd like to just mention is that the International Iron Metallics Association is developing a series of white papers looking at these various topics like low carbon EAF, what's happening, hydrogen-based DR production and so forth. And so you should see a series of white papers come out probably starting in the fall, if people are interested.
Thank you. Chris, could I just mention something briefly as well? I was a bit embarrassed. My last slide I didn't show, and the last slide was saying, thank you to Sarah Hornby, who listened to all my arguments and went through them one by one, and I forgot to say thank you to her. So Sarah, thank you for your advice and help. And as many of the committee would know, she's very knowledgeable on these areas. So thank you.
And to Jeremy's point, yes, Anna has a way of capturing all the questions, and we can certainly circulate those to the panelists so you can follow up on those as you see fit. So on behalf of the AIST then, thanks for being part of this very interesting event, and have a good day further or morning. Bye.
Thanks, guys.